So as my good colleague Henrik previously mentioned, my name is Bob Martin. I am the Senior Applications Manager for Atmel based in San Jose. So the team I manage supports all of the field applications engineers in North America and around the world, but mostly focused on North America. And I'm also heavily involved in the maker community and education community, so I come out to maker fairs to help people with their designs. I'll sit down and help you architect with an Arduino or moving into an AVR or another microcontroller, a SAM microcontroller, ARM-based microcontroller. What I'm going to talk about is extending what Henrik was talking about in how the Studio 7 we're releasing on Monday will get you a level of visibility into Arduino debugging that was always there in the parts, but was tough to do up until now in terms of being seamless and allowing people that are familiar with your Arduino environment to actually take advantage of our development tools to do that. So the current situation for in the Arduino environment is applications are getting larger and more complex. And with with Atmel's focus on IoT, a large part of making an IoT application work well is generally they're battery powered. You need low power. And the standard executive infinite loop approach to those type of applications is not going to work anymore because you're going to end up burning battery. So you need to do introduce something called, it's technically called thread programming, and we're going to be coming out with app notes and more information on how to do that. But when you start looking at the thread programming and the low power modes that are already in our microcontrollers that the Arduino environment hasn't really taken advantage of, but we're adding that, working with Arduino, you need to start getting at the debug visibility that we're offering now through our tool chains. So everybody knows about the current debugging mechanism for Arduino. You've got, well, one and technically two, right? Serial and serial print line, okay? You're basically putting in breakpoints, visible, printable breakpoints, you know, serial print line, I'm here, now I'm there, now I'm there, which is great. It gives you, it's a very high level debug facility. There's no learning curve. You just put your string in quotes and you can print a variable or whatever. Needs no extra hardware. It's coming through the terminal emulation of the USB connection or whatever to your Arduino board anyway. And again, you can customize the information. Again, you can print states and the values of variables and whatever you've got coming out. It's great. It's a great debug facility. But it has costs. And I use the term time and space when I talk about debugging. It takes time because depending on the baud rate that you're running, the serial print line can be a thread blocking situation where it takes the time to get those characters out the serial port. And yeah, you could get down to 86 microseconds per character at 115.2. Sometimes you can't push 115.2. At 9600 baud, you're spending 10 milliseconds per character, okay? Which means that if you're running a 9600 baud connection and you have a 1 millisecond timer that's an executive loop that's ticking off 1 millisecond, you've thrown away at 10 executive loop executions for every character you're putting out your debug port. So if you've got a control loop, you're shutting off your control loop for the amount of time you're printing that character out. There's got to be a better way to do it. The other thing, and the last thing is, okay, so that's time. Space is, we have to add all these debug statements. And then you can go F0 or however you want to create two, you know, on your code repository, create two branches and, you know, because eventually you're going to have to manually, you know, strip all that debug code out because it's taking up space in your final application. Either way, it's going to take you a little bit, especially if you're trying to just get that last little niggling thing down. You're going to end up spending a lot of time slicing stuff up with the serial print line. So there is a better way to do things. And I'm using this is kind of I took the Blinky example and I added the digital writes to port 8 are just on the either side of the serial print line in what says breakpoint 1. So if you count the characters, there's 10 visible characters, but it's a serial print line, so you get a carriage return and a line feed in for free. So there's actually 14. And again, on port 8, I hooked up one of my logic analyzers to port 8, and that's basically the time it takes. Now that's the time, it's probably hard to read on the screen, but that's a tenth of a millisecond, 0.13 milliseconds. That's 0.3 milliseconds that your system is offline, is doing nothing but shoving characters out the serial port. Doesn't sound like a lot of time, but in the microcontroller world now, it is. So, Atmel Studio and some very inexpensive debugging tools allow you to get at the very core of the microcontroller without relying on serial print line. You can walk away from serial print line. You can still, you can still use it. I'm not saying you can't, but how do we accomplish that? Well, it's not black magic. Okay, it is kind of a hidden debug feature, and Arduino is looking at adding the similar debug features, but I can't commit on Arduino's part. But they are discussing that type of debug environment within the Arduino IDE. But for now, what we're going to talk about is DebugWire. DebugWire is on the Mega 328P, is on the 32U4, is on every 8-bit microcontroller or an equivalent debug channel since we've been building them. We haven't been hiding it per se, but it's available, and it basically uses one pin, the reset pin. We clock everything in and out of the reset pin specifically. And that gives us full, complete access to the AVR core and all the peripherals on that chip through one pin. Other parts like the 2560, the Due, which is a SAM3X, and I forgot to move the upcoming Zero, the Zero is now out. We even have more advanced debug facilities built into those chips. But primarily, since the Uno and the 328-based products are the most popular out there, we're going to focus on DebugWire right now. So what do you need in order to get at this magic interface at a debug level? The green board on the left of the screen is a bare bones PCB version of what we call the Atmel Ice. It's available through our website. SparkFun is also selling it right now. And for around $35, plus some additional cables that you have to buy, that green board can debug and program any microcontroller Atmel makes, AVRs and the ARM-based products. The reason there is two connectors on the right-hand side is the pinout standards between an AVR and an ARM-based microcontroller are slightly different in terms of the debug headers. But apart from that, a micro USB cable and Atmel Studio is all you need. The package on the right-hand side, the white box, that looks kind of like an iPhone prototype, unfortunately, is the fully featured version. It costs between $90 and $99, depending on who's selling it. And that has all the adapter cables, and the little blue board toward the bottom there is the adapter that adapts to all of our debug boards, our evaluation boards, the different pinouts we use per se. We also, in conjunction with Arduino, but this is an Atmel board, designed and developed a debug shield for the Arduinos, which gives you direct access to the reset wire and allows you just to use the standard ribbon cable to connect the Atmel ICE, or the JTAG ICE 3 actually, to an Arduino. I'm going to demonstrate a connection without using that, but suffice it to say that this plugs into any Arduino, either the Mega form factor or just the standard form factor, and pulls out the full signal visibility without having to use the tiny little adapters to any Arduino board out there. So the connection formally looks like this. The setup I have on the bench right now is slightly different, but which I can show you that we can hook up the debug shield directly to an Uno. I actually have a red board, so I'm just going to switch video for a minute. So it's a little hard to tell, but here is the Atmel ICE, the bare PCB. This is a SparkFun red board. It's essentially an Uno clone. And you'll notice that with an adapter on the end, I'm coming directly into the ICSP port, because the ICSP port not only connects the SPI lines, which is how the normal bootloader, or how we normally image the bootloader, but it also exposes the reset pin on that connector, which allows me to get at that debug channel directly through that connector, okay? So let me go back to the software, and as Henrik mentioned, this is, on Monday, we are launching Atmel Studio 7. The previous version, Atmel Studio 6.2, is still on the website, it's still available, and you can still do what I'm about to do now, or in my live demo, is import a sketch and debug it. But this type of action now is seamless in Studio 7. And we're gonna drive a live demo. I'm just gonna show you one more screenshot, because we added a function down here where you can see under new project, I now have an Arduino symbol that allows me to drive, or sorry, not drive, but import a sketch directly. And now, let's just do that in live demo terms. So just like the cooking show, I magically have Studio 7 already sitting there. So this is Studio 7, and what I'm going to do is I'm going to define a new project. And under the new project, I'm going to select create a project from Arduino Sketch. I'm going to call it Blinky 2. I'm going to go down into Blinky. Now it's going to ask me, where's your sketch file? So I'm going to go browse. I'm going to go up, down into sketch, a blink test. It doesn't matter, it doesn't have to be the same name. The board is the Uno. That's the SparkFun red board is essentially an Uno. And the device is a Mega 328P, and it's good to see that the tool guys agree with me on the board. What it's doing now is it's importing the Arduino sketch, and it's going into the Arduino IDE, because it knows through the past that the Arduino IDE, and it's bringing out all the libraries and C++ files that make the Arduino environment the Arduino environment, okay? In terms of pure C++, this is what a Arduino sketch looks like. You may recognize now what all that we've added is another header file, Arduino.h. We've added some prototypes for setup and loop, but here is essentially the sketch, right? Recognize it? Setup and loop. Everybody recognizes setup and loop. Well, all these other files, all these C++ files, when you build an Arduino sketch, these are all the files that are being compiled and being dragged along for your sketch, which makes that whole API possible. right? Arduino abstracts all of the low-level functions for you and gives you that nice, clean, easy-to-use API. Every Arduino sketch you build brings in all these files. I'm going to go down, and for those of you who are familiar with C++ or C programming in general, there is main.cpp, right? If you're a C programmer, everybody's got main.cpp. Well, remember an Arduino sketch, setup's called once and loop's called continuous. Here is the code that does that. There's actually an init and an init variant, which is stuff that's hidden by you, because that's called depending on the board you're using, whether it's an Uno or a Due or a Leonardo. But here is the executive loop. Actually, here's the call to setup, okay? And here is the infinite loop that calls loop, okay? That is actually where a sketch starts executing from, okay? There is the guts of an Arduino sketch right there. And we have that type of level of visibility. So, how do we start debugging this? I'm going to build it, but I'm going to do something first to allow even more visibility. So, as silicon vendors, as microcontroller vendors, we work with compiler vendors, and the compiler people look at chip architectures and they figure out how to optimize code. They figure out how to take these C statements and turn it into machine language that's as small as possible, because you don't want to waste space, obviously. What that does, though, however, that's called optimization. What optimization does, however, sometimes is makes debugging harder, because it plays tricks with the microcontroller core, and instead of storing a variable in RAM, it'll just keep it in a register, and it makes it harder for debug environments to trace this. So what I'm going to do is I'm going to set the optimization level all the way to nothing. It's called -0, which means don't do anything, which is going to make your code bigger, but you can selectively, as you get more advanced, you can make modules that you have debugged, you can build them really small with high levels of optimization. You can build other modules and compile it with no optimization, so you maximize your debug visibility. So I'm going to build it. This is the same compiling process that happens under an Arduino environment. It just looks a little different, but when you do the upload sketch and you see all that stuff rolling by, these are the same steps that's going through. They use the same GCC compiler we use in our toolchain. Again, now we built a file that's 6,700 bytes, almost 6,800 bytes. We're using a little over 260 bytes of RAM to do this. Seems like pretty big to blink an LED, but I'm going to recompile it, optimized for size later on. But now, here's what you can't do in the Arduino environment. Oh, I need to select a debugger. That's better. This blue play pause symbol up in the corner here is download a sketch and then run it. And I have to do some little hoops here to enable the debug wire, which I've just done. So by default, as I said, debug wire uses the reset pin. But when we ship the parts, the reset pin is just the reset pin, okay? In order to turn on debug wire, that little sequence of windows I went through basically said we go in and we program and we tell the AVR, or the Mega 328, don't use the reset pin as the reset pin, use it as debug wire. So that was that whole sequence of events that I went through. What I'm sitting at right now is the blink application sitting, waiting to be executed from main. Okay, I'm going to go to the Blinky sketch. Oh, no, Blinky sketch.cpp. And I'm going to put something you can't do in Arduino. I'm going to put a breakpoint right there. That little red dot, that is an execution breakpoint. I'm going to run. I ran my sketch up to that first statement. Okay? No serial print line. I am now sitting and I can look at, I have complete exposure or complete visibility into the Mega 328 right now, including the actual disassembly of the AVR code. That's the actual AVR assembly code that's doing all this. That's the last stop before the raw binary of that core executing. All right, so, but the interesting thing is I'm going to put a breakpoint. Actually, I don't need to put a breakpoint there. I'm just going to execute to the cursor. What? The processor is held in reset. It's stopped right now. The core is, what? It's not, it's frozen. And I just ran, I told the processor now to run to the beginning of that line. You have complete run-stop control, right? Now, for those of you, pin 13 is the standard. That is where the LED is on every Arduino board, right? Pin 13. Pin 13 is actually port B bit 5, all right? And when you go pin mode 13 output, what you're actually doing is you're setting the data direction register for port B pin 5 to an output, right? We're going to go look at port B directly. Under I/O, now I have direct visibility into every peripheral on that part. I'm going to go to port B, and lo and behold, the data direction register on bit 5 has now been set. Okay? I can now manually turn on the LED by myself. And what I'm going to do is I'm going to toggle this bit right here, which is, that bit, which is port B. So there's 3 registers on a Mega 320, on a Mega 328. There's 3 registers that control a port. There's the direction register, which is the middle register in that line, which tells you if it's a 1, it's an output. If it's cleared, it's an input. The top one pin is what is the level on that pin, regardless if I'm an input or an output. The bottom one, called port B, is if I'm an output, if I write a 1, then that output goes high. I'm going to hold the board up so you can see. If I click this, the blue LED came on. So now in this instance, I have direct and absolute control of that part while the sketch is running. I stopped it. That sketch is still in Flash. And if I hit run from here, it'll start blinking that blue LED. But the point is, I went in and I manually superseded the setting. So when you're developing that code, you're going, there's something wrong with that hardware. I've got this zero print line. You can put a breakpoint right after you call that library init function, and you can go in and look at the registers of that part, right? You can look at the timer counters, and you can go, I'm looking at the data sheet, and that bit right there shouldn't be set. You can step through the code and find out who's setting that bit. And knowing that that bit maybe has to be cleared, you can go in and clear that bit manually and then keep running to confirm that that is in fact the problem. Okay, so this is a level of visibility that you're going to need as you start developing more complex applications. right? And as you saw, I pulled in a sketch seamlessly and translated. And you can get in here, and the other thing is, okay, remember when I said that project was pretty big? It was 6,700, right? I'm going to do one more thing. I'm going to now build an Arduino sketch at a level of optimization that you can't do in the Arduino IDE right now. Oh, I have to, and it goes, it's all grayed out. What's going on? I can't change all these options while it's in debug mode. So if I pull it out of debug mode, it's just going to start running the program while I go off and do things with my software. So there's an optimization called Optimize for Size. And this turns on the people who wrote the compiler, and I need to step back a little bit. The two gentlemen in Norway who designed the AVR core, which is what all the megas are based on, worked with compiler vendors to make the instruction set extremely friendly to C compilers, which means that when we turn optimization on, a lot of magic happens to make that code as small as possible. I'm going to rebuild this at the highest level of optimization for size, which means it's pulling every trick in the book to make that code smaller. I cut that code size, it's less than half as big now. I didn't do anything. I didn't change the source code. I didn't change the sketch. I just changed the compiler optimization level, and my sketch is now half the size. Right? That's so that's a significant. If you just need a couple hundred more bytes, you can use Atmel Studio to build the sketch at this higher level of optimization. All right? So I can demonstrate this again. We have a booth over here in the big tent, the makerspace. I can show you this in real time and walk through the array. Again, this is Arduino's magic. All these C++ files come along for the ride. When you start getting more tuned to the actual debug environment and the raw C environment, you know you can start removing some of these files and making that sketch even faster. And then essentially you can migrate at your own speed from an Arduino sketch environment to a pure C++ environment and only bring in the stuff and the support facilities you need and not only shrink the size of that code down, but improve its performance. All right, so on to, there's a couple other things that I want to close talking about. We have a board, it's called the 328P Explained Mini. It comes with the header outline for an Arduino, but we don't put the connectors on it. It costs about $9, $8.88. We are not undercutting Arduino. We are not getting in competition with Arduino by selling this underneath Arduino, given that we supply chips to Arduino. The point of this board is when you're transitioning on this board for $9-ish, we have the embedded debugger on it. So everything I was doing here, you don't need the external board. All you need is a micro USB cable. You can turn this board into an Uno. You can download the bootloader and then download sketches to it the normal way. It looks like a Nano when you download the bootloader, and you can run ordinary sketches. There is a caveat on it. The board only handles 5 volts. There is no linear regulator, so if you plug a 12-volt battery into this board, it's going to let all of Atmel's magic smoke out of the 328 and the embedded debugger, and then you'll have to buy a new board. But apart from that, the point of this board is if you have an Uno-based application and you need to do some advanced debugging, with the header kits, which I think are $1.99 or something like that, you can replace your Uno with this board and sandwich it into that debug environment, and you can replicate that exact debug environment that I was just showing with Studio 7. It's called a sneak peek, but it's not really a sneak peek anymore. The Arduino Zero is now in full production. And the reason it's not called the Arduino tray was announced 2 years ago. So, right, it's the Italian counting, uno, do, tray. I think you got it. Why do we call it the Zero? Is it a downgrade? No. It's called the Zero because it's based on our SAMD21 chip, the G18A, which is kind of irrelevant for this talk. This is a Cortex M0 core running at 48 megahertz, which is so much more than 4 times the speed of a 16 meg 328 because it's a 32-bit CPU. So the amount of data this thing can gulp at one time is 32 bits wide. So math that you couldn't do on a Mega, like matrix multiplication, now you can do on this guy, all right? The Zero, when we helped design it with Arduino, we also threw in the embedded debugger for you. So you can do all that advanced debugging on the Zero, just like you can on that Xplained Mini, that board that I had. Again, on the Zero, you have all that advanced debugging facility there for you already, which is when you start debugging complex ARM applications, you'll understand the usefulness of having a source-level debugger. It is a more complex core. The D21, again, is completely, at IDE, Arduino IDE version 1.6.5 is fully supported. You can take your Blinky sketch and download it, and you'll blink an LED. But if you're using a 48 megahertz Cortex M0 to blink an LED, you might want to go back to the Uno. This is, again, a part that's got USB on it. It has some really advanced timer functions that we're going to be extending into the Arduino library. It's got, again, native, it has its own USB port. It's USB capable both in host and device, as apart from some of the previous AVRs that can only do device. Full speed only, but host and device. Anyway, that is about all I wanted to say in this session. So again, if you want to talk more about advanced debugging and how this all works, I'm at the Atmel booth all weekend. And if there are any questions, I can take some of them now. We got some time. All right, thank you then.